Hello everyone, and welcome to Microtrac's free webinar, Optimizing Your Shale Fracking Extraction Rates. Your speaker today is Terry Stauffer. Terry works closely with Microtrac as a particle characterization specialist, and he has over 40 years of experience in the industry. Today's presentation will include information on hydraulic fracturing and proppants, which are also referred to as sands. We'll go over which geometric properties are important to proppants and which methods have been traditionally used to measure these properties. Finally, we'll discuss the advantages of automated 3D image analysis with some examples. And at the end of the presentation, we'll be answering your questions. So without further ado, I'll turn it over to Terry.
Thank you, Claudia, and welcome to our discussion today. So let's get started. Hydraulic fracturing. Most of you know this drilling practice pumps a combination of high-pressure water and fracking sands, or proppants, along with small amounts of chemicals downward and then horizontally through natural gas-bearing shale, or straight down and deeper through petroleum-bearing shale. Proppants are small sand, or more rarely ceramic particles, which keep the fissures propped open for smooth flow back to the surface. Here a typical gas well is diagrammed on the left, and a closer view of the fissures being opened from the main shaft through the shale is shown on the right. And here's a diagram showing the proppant in the shale fissures, keeping them propped open for good flow back to the well surface. Proppant characteristics. Ideally, proppants would be lighter than water, stronger than diamond, cheaper than dirt, and readily available, which of course they are not. Realistically, premium proppants do exist and would have a narrow size distribution, high strength, and be round and smooth. And inferior proppants with broad size distributions, low strength, and flat and angular in shape should be avoided. The various types of proppants include sand, ceramics, and resin-coated sand or ceramics. Sand is least expensive and the most used proppant, but has shape characteristics that limit the gas flow conductivity compared to other types. It has moderate strength, and fines are generated if particles get crushed. Synthetic ceramics are more expensive, have superior shape characteristics compared to sand, and come in various strengths depending on grade. The resin coatings on some sands and ceramics have no real effect on strength, but they do prevent fines from being released into the fissures if the particle is crushed. Curable coated proppants bond together to form physically strong links when subject to high pressures and temperatures, preventing proppant flowback. Proppants make up about 10% by weight of the fracking fluid pumped into the well. Three types of proppants are shown here: a high-strength, narrow-size, high gas flow conductivity ceramic at the top of the pyramid, then a medium-strength, broader-size, medium conductivity resin-coated ceramic, and a lower-strength, lower conductivity sand at the bottom. This slide refers to the official test requirements for proppants as set forth in the American Petroleum Institute's current API-RP 19C standard. It provides size distribution ranges and two geometric shape factors that must be measured and reported, among other properties such as crushing strength. The size fractions range from 3.35 millimeters down to 106 microns, in a number of different smaller size fractions depending on grade of the proppant. Details are on the next slide. The Krumbein-Sloss chart shown here are on the next slide, developed in the 1960s, showing example silhouettes of combined roundness and smoothness of a small sample of 20 particles is subjectively measured by a technician on a manual microscope. More of these shape factors and others can provide more plentiful and representative information, which will be discussed later. This slide is a table listing the API's required size fractions to be measured for proppants. The table establishes sieve sizes for use in testing designated proppant sizes for different grades. It should be used as a guideline and doesn't attempt to preclude the use of other grades that are or can become available. In addition to the size requirements, there's a requirement to visually estimate two size parameters and shape parameters of sphericity and roundness. Here's the Krumbein-Sloss chart for estimating those shape parameters for proppants, both sphericity and roundness on a scale of 0 to 1. A value of 1 for each parameter would represent the best shape for a proppant, a perfectly smooth sphere. This shape would maximize the flow through the shale fissures. But the current official API procedure for making this measurement is decades behind the existing technology of automated 3D image analysis, which could make these and many more shape measurements on thousands times the existing sample size requirements in minutes with no operator visual subjectivity. Note at the bottom of the slide, the standard actually states visual estimation. The procedure for estimating sphericity and roundness of proppants by using the Krumbein-Sloss chart uses a 10 to 40x magnification microscope and a balance with an accuracy to 1 milligram. The technician records the weight of each fraction, then chooses 20 particles at random and observes them microscopically and estimates their shapes relative to the images labeled with values on the chart and reports those shapes to the nearest 1/10. Automated 3D dynamic digital image analysis is now an accepted alternate procedure for both the size distribution and the shape measurements for proppants. This offers major advantages, saving significant time and cost and improving measurement accuracy by making a single measurement of one large sample. And here are more advantages of 3D image analysis. Actual measured sphericity and roundness of all individual particles in each size fraction rather than visual estimates of 20 particles per size fraction. It eliminates operator error and subjectivity, and it reports some 36 different size and shape parameters, some of which can complement the sphericity and roundness values and help define tighter specifications. Here's a schematic which shows the simplicity of dynamic image analysis as used in the PartAn 3D analyzer. The dry sample placed in the funnel above right moves on a vibratory feeder to the edge of the sensing zone, where it falls by gravity through the sensing zone and is collected in the sample box at the bottom. A light strobe on one side of the sensing zone lights the particles as the digital camera on the other side photographs the particles as they tumble through the sensing zone. A video file of the analysis is stored, and distributions and summary data for 36 morphological parameters for each particle are calculated and reported. And all this data is available as soon as the analysis ends, typically in less than 3 minutes. This is an open instrument photo of the analyzer. The particles are seen tumbling through the sensing zone on the left, while the strobe and camera record the video file of the analysis. The video file can later be recalled and rerun under different measurement conditions, or overlaid on a graph of a series of historical data. The image analysis technology could hardly be more simple or more robust. The next set of 5 slides illustrate the software advantages of 3D image analysis for proppants. This one is the XY graph, which is displaying the volume size distributions of the 3D length, the red curve, width, green, and thickness in black, in differential frequency size distributions. Up to 6 of the 36 parameters can be displayed here on this graph at one time, or historical records of the same parameter can be called up for comparison purposes. This PartAn graph shows the Krumbein-Sloss sphericity and roundness shape factor calculations plotted relative to their values for each size fraction measured. Curve 1 is the sphericity, with values running from about 0.87 to 0.99. Curve 2, roundness, runs from about 0.46 to 0.84. And this is the tabular PartAn data for the measured sample. The column at the left is the list of size fractions in microns, and the next 3 columns are the 3D length, width, and thickness size distributions by volume %. The last 3 columns are roundness, call out 1, sphericity, call out 2, and count 3 by size fraction. The count column lists the number of particles measured in each size fraction, far more than the 20 particles in each size fraction measured by manual microscopy. This slide is a size plot of the PartAn's Sieve parameter, which can be calculated from the 3D measured sizes and which reports the same size distribution values as the actual Sieve data. Note the PartAn Sieve parameter curve directly overlies the actual manually entered Sieve values, with the option to show mesh sizes on the x-axis. This feature allows the user to continue reporting the data in their Sieve format if they desire. This slide shows data from a processed sand, and an unprocessed sand will be shown on the next slide. This is the PartAn scatter diagram window. This blue window shows the location of every particle in the sample relative to each of its Krumbein shape parameters, sphericity on the top x-axis and roundness on the right y-axis. Any one of the PartAn's 36 3D size or shape parameters can be plotted on either one of these graphs. Summary data for each of these parameters on this processed sand sample are listed in the column at the right. Note the sphericity and roundness values for each parameter meet the acceptable API specifications, both greater than 0.6. And these parameters were actually measured on over tens of thousands of particles rather than visually estimated on a random sample of only 20 particles by an analyst on an optical microscope. The darker the blue in the scatter diagram, the higher the particle concentration. The bulk of the sample population can be seen in the scattergram to be within the API specification limits. On this next sample of unprocessed sand, the roundness specification is too low for the API standard at 0.52 instead of greater than 0.6. And this is actually measured roundness on over 160,000 particles in this sample. This would be a very difficult distinction to make on 20 particles by manual visual inspection. The inspect values of the previous samples are given in parentheses here. This is the View Particles window in the PartAn software. This contains the full scrollable image file of the particles measured, and it's saved as a video file which can be rerun later under different SOP conditions. It can also be printed and exported in both image and data formats. The image file is shown sorted in descending order on a length parameter with the length value displayed under each image. Shown also is the particle query window where a search for particles with various parameter limits can be made. The current query shown here will list all images and their respective distributions of particles with a sphericity and a roundness greater than the Krumbein minimum value of 0.6. It will also report the percentage of those particles in the sample. Microtrac offers two different PartAn 3D dynamic image analyzers, shown in this slide. At the left is the PartAn 3D Pro, short for process, showing a unit mounted on a process pipe sampling and measuring the process stream and returning it to the process. The turnaround time averaging about 10 minutes, which greatly improves process control response time with a normal increase in both productivity and quality versus having to collect the samples manually, bring them to the lab, and then make the measurements. On the right is an R&D or QC lab bench model, which also has an optional auto-sampler accessory for continuous unattended measurement of up to 24 samples. Microtrac has over 80 online process image analysis systems like that on the left, installed in a variety of processes. In summary, optimal proppant size distributions and key shapes provide maximum convection flow rates of shale oil and gas flow back to the surface. Traditional techniques for measuring these properties are very time-consuming manual operations on small and very unrepresentative samples subject to operator error. Sieves and manual microscopy measurements can now be replaced by rapid automated image analysis on very large samples in just minutes.